I'm Nick Deligiannis. I am a PhD student at the Department of Control and Computer Engineering of Politecnico. And as a member of the CAD group, I work on topics related to test and reliability of digital circuits. Now, it's a pleasure of being here, albeit virtually, to briefly discuss about my topic about functional stimuli generation for burn-in test. Now, my speech is divided in 5 sections. One, introduction to the problem, the general area of the burn-in test and some terminology around it. Then we have some semantics for the modeling of the problem definition, and of course, the proposed method to optimally solve the problem along with some experimental results. And lastly, some conclusions and reflections about the overall work. So let's begin. Now, what is the burn-in test? Burn-in, or BI as it is abbreviated, is an end of manufacturing procedure that is typically performed right before the final system level test. Now, it is the main countermeasure in the arsenal of a test engineer in order to combat effectively the infant mortality phenomenon, which is modeled by the bathtub curve, as we can see here, which is very problematic. Now, in the infant mortality, we observe that we have a significantly high failing rate of the devices during their very early life stages. And this is typically due to some latent defects being present. To mention that in the safety critical domain, like for example, the automotive, the aviation space, the biomedical sector, and so on, in the examples, for example, that Juan mentioned previously, the burn-in test is omnipresent. It is always performed. During burn-in, the devices under test, or DUTs as they are abbreviated, they are placed inside specially created climatic chambers where they are stressed up to their specification limits by increasing the temperature and the voltage, that is the static form. So we have external stress sources. And also on top of that, we can force the DUTs to execute some stressful code, some stress-inducing stimuli. And this is the internal stress, which increases the switching activity of the circuit, the toggling of the circuit. This is the dynamic form of BI. The result of the burn-in procedure is that we have an artificial aging, which effectively eliminates the infant mortality period, and we can discard the faulty products. A couple of hours or days in the climatic chamber are equal to months of operation for the devices, and so we can age them quite effectively. Now, up until recently, the most common form of burn-in test was in static format. However, with new technology nodes where in the same silicon area we have exponentially more amount of transistors, which result to denser circuits, the static burn-in is no longer effective because it cannot fully sensitize all internal parts of the circuits. And also, with the static burn-in, we do not age the circuit in the way that it was supposed to be in the mission phase. So it is not aging in a functional manner, so to speak. And so the burn-in test evolved into new forms like the dynamic burn-in, the monitor, the testing burn-in, where a common thing on all of these procedures is that we need the appropriate stress-inducing stimulus to stress the device in an internal manner. Now, this is a problem. And how do we do that? How do we solve it? We have two schools of thought. On the one hand, we have the structural means, which means that we can rely on top of some pre-existing design for testability infrastructures in the circuits, like, for example, the scan chain, some boundary scan, and so on. And we can perform the application of some specifically crafted patterns, which are applied with a goal, for example, to toggle each net of the device at least once, and then repeat again and again. Because as I mentioned, the burn-in typically lasts for hours and even days. It's a very long procedure. We have to be very careful here because, again, by the structural means, we are not aging the devices in a functional manner, and it is possible if we are not careful to overstress the devices, which can then end up with some artificial yield loss. On the other hand, we have the functional means. And here we task a group of test engineers, for example, to generate some low-level program, some stress code on some language, with a goal of maximizing a stress metric when applied on the DUT. We will speak about the stress metrics in a second. Now, the benefits here is that we have at-speed application of the code with respect to the structural means in which the circuits operate at test speeds, which is a lower frequency. And also with the functional means, you cannot cause any kind of damage to the DUTs. So when comparing the two methods, it has been observed that by relying to functional means, it is possible to increase the temperature in certain hotspots, in certain spots of the DUT, so in a much higher way than in the structural means, so with scan, for example. And so it can be more effective in terms of generating heat gradients on the devices. Now, let's see how we do this. Initially, we have to quantify the stress. Stress is pretty vague as a term, so we need some stress metrics. Typically, they fall in one of the two categories. We have the single point metrics, in which the DUT's nets are considered separately, one by one, and we try to generate stimuli that switch the nets for as many times as possible, or at least once, as we saw previously. On the other hand, we have the multi-point stress metrics. Here, we dissect the DUT into neighborhoods or groups of nets, if you will, based on, for example, minimum distances. And now the goal becomes that for each neighborhood or group of nets, we try to find a sequence that causes all possible switching permutations to occur when executed by the device. Then we concatenate all these sequences and we end up with a big stress program. Now, in my work, I have worked primarily on the second category, so the multi-point metrics. And we have the following two. Initially, we have the repeatable and constant switching activity maximization. Now, here, the goal is that on the stress target that we have, we need to identify a pair of two instructions that induce the highest possible amount of concurrent nets to switch when executed by the device. Let me explain with the finite state machine. So we have the initial state. The circuit is driven in an initial state that is well defined. That means no X values are present, no nothing. Everything is initialized. And from that state, by applying the sequence, the first instruction, so I1, we move to the state B, in which as many as possible nets have performed the transition from 0 to 1 or from 1 to 0. Then from the state B, we move back to the state A by applying the second instruction that inverts, let's say, the transitions induced by the previous one. So in this way, we can have an arbitrarily large amount of stressing for the target until it is forcibly terminated, let's say, by issuing some sort of interrupt. Then on the second hand, we have the multi-point switching activity maximization of size 2. Here, we dissect the DUT, as I mentioned previously, into neighborhoods of size 2. So we have 2 nets per neighborhood. And the grouping is performed by minimum distances that are computed by the layout topological information of the circuit. So this must be present at this stage. And now, for each of the neighborhoods, we start from an initial state, and we try to find the sequence that causes all possible switches for both nets to happen. This is performed for every neighborhood of the stress target. Let's see how we do this. We rely on formal methods, or FMs, as they are abbreviated. And the formal methods are practically rigorous mathematical tools that are very much liked because they offer optimal solutions. Now, the goal here is to reduce the problem to the problem of the Boolean satisfiability. So to move of the domain of the digital logic to the propositional logic. This is performed by getting the gate level form of the circuit and by performing what's called circuit unrolling on top of symbolic simulation. We are able to extract the Boolean formula of the circuit. So the function that every circuit implements a Boolean function. We are able to extract this function, but this is done in a conjunctive normal form. This is an equisatisfiable formula with a Boolean formula of the circuit. But in this format, it is able for formal method tools to digest them. So the SAT solvers, for example. So we have extracted the Boolean formula of the circuit now. And on top of this formula, we have to enforce constraints in the forms of clauses, as they are called in the terminology, that practically make the SAT engine to know which is the functional scenario. We are interested in functional code here. For example, the SAT solver is completely agnostic about any kind of instruction set architecture. What kinds of, if we speak about, for example, processors, what are the instructions that are supported and so on and so forth. So we need to constrain the respective bits, and the CNF is extended with every kind of functional constraints that we have. If someone has the applications or mission profile of the device, this can be also applied here, for instance. When this is done, then we leave it up to some sophisticated tools like the SAT solvers or max SAT solver or bounded model checkers according to the stress metric that we have encoded, and we get back some model or solution for the problem. Now, from that solution, we are in the domain of the propositional logic, I remember. So we have to move back to the digital logic and generate some practically patterns, 0-1 logic. It is able to do though because we know the mapping from variables to literals to nets. And so we can construct, for example, assembly programs by disassembling, let's say, the formula. Let's see the experimental results. For the first metric, the repeatable constant switching activity maximization, we have applied the method on two RISC processors, the OR1200 and the RISC-V risky processor. And as stress targets, we used the ALU's 32-bit adder, the decoding unit, and the load store unit. Now, to have a mean of comparison, a baseline comparison, we have performed the profiling simulation on a test program or software test library. STL is the abbreviation. And on that profiling, we identified the pair of instructions that cause the maximum switching for each of the stress targets that we have considered. As we have expected, for both of the circuits considered, the formal method's solution outperforms the segment extracted by the software test library. When it comes to the second metric, the multi-point switching, we once again have the software test library to compare with. As stress targets, we have the 32-bit adder and decoding unit now of the risky processor. But here we have also performed scan insertion. So we have converted the processor to the scan equivalent, and we have performed some ATPG. And with the simulation of the ATPG generated patterns, we were able to find the highest switching induced by a non-functional scenario, so the non-functional approach. Now, similarly as before, the formal methods outperform the software test library, so they induce better switching, so they cause better switching permutations to the net pairs. But as we can see, there is a deviation from the non-functional scenario. Now, for these small numbers that we see here, relatively small, however, we see that we are able with structural means to switch or control some lines, some nets that are not controllable in the functional scenario. Because if they were, the formal methods providing always the optimal solutions would have identified it. So probably these lines will end up to some functionally uncontrollable faults, which won't be considered in the mission phase or will not be problematic, will not be able to produce any system failure. In the context of the ISO 26262, for example, for the autonomous vehicles, this would most probably be some safe faults, which will be removed from the computation of the fault coverage. Now, the final remarks, the conclusions here is that the burn-in test is the most effective tool we have to combat the infant mortality. And the infant mortality is a very important problem that typically comes with every new generation of integrated circuits. The static means of the static format of the burn-in test is no longer effective. So we need a combination of the static and dynamic format. However, we have the problem that the stress-inducing stimuli cannot be easily generated because they take a lot of manual labor. However, if we have a well-defined stress metric, we show that it is indeed feasible to automate this process and produce some high-quality stress solutions. As a final note, to say that albeit the method was applied on processors, being the test cases here, there are no limitations to, or let's say, limitations of the method, and depending on the processors being the underlying circuit, and that can apply to any kind of sequential circuit, given that you have a sufficient amount of specifications to constrain the problem appropriately. That would be all. Thank you.